This is the V2, the world's first long-range guided ballistic missile. Faster than 4 times the speed of sound, it even traveled to the edges of space before descending to its target, and it was the first man-made object to leave the atmosphere, reaching a height of 128 miles above the Earth. The V2 was a revolutionary weapon, unlike anything the world had seen before. In this video, we'll break it down in detail and explore whether it really had the potential to change the course of the war. In this film, we'll show the basic combat model of the V2 rocket. My name is David Webb, and this is Blue Paw Print. The V2 was a single-stage liquid propellant rocket with a complex guidance system. It was 45 feet 11 inches long, with a fuselage diameter of 5 feet 5 inches. Its wingspan was 11 feet 8 inches. The fuselage was built using thin sheet steel wrapped around a solid framework of steel. Fuselage components were connected to the steel framework by welds and rivets. Fully fueled, the V2 weighed 27,557 pounds. The V2 missile was composed from 4 main sections: the warhead, the equipment section, the center section, and the tail section. The warhead section was mounted at the rocket's tip, complete with its explosive charge and fuses. 3 fuses were fitted into the warhead. A contact and inertial fuse were mounted right under the nose cap, and a second inertial fuse was mounted at the base of the charge. Any single fuse could activate the explosive charge. The warhead was loaded with 2,000 pounds of amatol, a highly explosive material commonly used during World War II. Amatol consisted of 60% TNT and 40% ammonium nitrate. Amatol was less powerful but cheaper and more heat tolerant than pure TNT. The equipment section housed the guidance and control systems. Inside this section were 2 electrically powered gyroscopes, which enabled autonomous control during flight. The horizontal gyroscope detected deviations in the rocket's pitch, while the vertical monitored yaw and roll. An analog computer connected to gyros and control surfaces, batteries to power the gyroscope's computer and other systems, and a main electric distribution board which could receive external electrical power before takeoff. In addition to the instruments and the batteries, the equipment section housed compressed air bottles to maintain pressure in the fuel tank, located in the central section below. The largest section was the center of the rocket, inside which there were 2 aluminium-magnesium alloy tanks. The larger of the 2 tanks held fuel, while the smaller one was filled with supercooled liquid oxygen. Both tanks were insulated with layers of glass wool that was pressed with wooden chocks to keep the insulation in place under heavy acceleration. The bottommost section was the tail, which contained the rocket engine, the adjoining turbo pump assembly and plumbing, as well as an exhaust thrust nozzle. 4 large stabilizing fins or wings protruded from the tail section. Each was equipped with a set of external and internal control vanes for controlling the rocket. These would be controlled by the analog computer. The details of the V2's launch and flight sequence will be covered later in this film. The V2 needed to have a powerful engine to deliver its 2,200-pound warhead up to 200 miles distance. It was powerful enough to produce 55,000 pounds of thrust for more than a minute. However, for this to be achieved, the engine had to consume a lot of fuel at very high pressure. German engineers designed an improved combustion chamber and pressure pump to meet these challenges. The combustion chamber was the core of the engine. The chamber had a double-walled structure with both inner and outer walls made of pressed steel. Fuel lines were fed through the double wall to the injector head. The fuel absorbed heat from the chamber walls. This helped cool the walls of the combustion chamber while also heating up the fuel. The injector head, consisting of 18 burner cups, fed fuel and liquid oxygen into the combustion chamber. The burner cups were also referred to as diffuser cups and were arranged in concentric circles. Each cup had a central liquid oxygen injector surrounded by 5 rows of fuel injectors and feed holes connected to the chamber's double wall. The fuel evaporating from the cup walls gave them some protection against high temperatures. As well, 4 rows of feed holes were drilled into the combustion chamber to give further protection from hot gases. If too much fuel was pumped into the space between the double wall design, the pressure could lead to a catastrophic explosion. To counter this, a valve would release high pressure between the walls before it could reach dangerous levels. The supply of fuel under high pressure was provided by a special turbo pump. The turbo pump was, in essence, a steam turbine that drew fuel and liquid oxygen from the tanks and fed them into the chamber through separate valves. The liquid oxygen valve was connected directly to the burner cups via 18 pipes. The fuel valve directed the fuel through 2 large pipes which split into 6 smaller sub-pipes before connecting into the inlet manifold at the bottom of the chamber's double wall. Steam produced from a steam generator powered the turbo pump. The steam generator, its fuel tank, and the turbo pump were all mounted to a frame attached to the combustion chamber via 4 large bolt joints. The V2's rocket engine was fueled by a combination of alcohol and water with liquid oxygen serving as the oxidizer that enabled the fuel to burn. The primary fuel, labeled B-Stoff or B-Stuff in English, was usually a mixture of 75% ethanol and 25% water. The fuel tank had a capacity of 8,179 pounds. Below the B-Stoff tank was the A-Stoff tank, a 10,802 pound tank of liquid oxygen. The liquid oxygen tank still needed to be continuously topped off right until the launch, as it evaporated very quickly. The rocket also carried 385 pounds of T-Stoff, a mixture of 80% hydrogen peroxide and 20% water, and 48 pounds of Z-Stoff, a mixture of 33% sodium permanganate and 66% water. T-Stoff, in combination with Z-Stoff, decomposed into oxygen and steam to drive the 580 horsepower turbo pump. Finally, P-Stoff, a label used for both compressed air and nitrogen, was used to fill special tanks throughout the rocket assembly to service various components and maintain pressure inside the fuel tank. The fuel was loaded into the rocket only after it was positioned at the launch site. V2 missiles were stored in protected bunkers, empty and without the warhead mounted. They were transported to their launch points using a special trailer called the Meilerwagen. The Meilerwagen was usually towed to the launch site by a 100 horsepower wheeled tractor, the Hanomag SS-100. The Meilerwagen was an ingenious design that could move the rocket to the launch position and elevate it to set the V2 upon the launch table. Once the Meilerwagen brought the V2 to the launch site, it was placed on the firing table or Abschuss platform. Although the V2 could be launched from a permanent platform, it was mostly operated from the firing table. This was a robust portable structure from which the V2 could be launched to the skies. Constructed from welded steel and weighing 3,600 pounds, the firing table had the necessary strength to support a fully fueled V2 rocket. The table consisted of 4 adjustable legs that allowed it to be leveled on uneven surfaces. On top of the legs was the support tube with a turning ring and rocket support pads that could hold the V2 upright. Under the turning ring at the central section of the firing table was a pyramid-like structure called the blast plate or blast deflector. Equipped with a hardened steel tip, the blast deflector was sturdy enough to withstand the intense heat and force generated by the rocket. Thanks to its shape, the blast deflector dispersed the exhaust gases laterally, ensuring that there would be no gas buildups that could threaten the V-2's balance during takeoff. Once the rocket was precisely mounted, it would be released from the lifting frame's clamps and turned 90 degrees left with the help of a turning ring. The Milewagen could then be moved in small adjustments. With the lifting frame still raised, the crew opened the retractable platforms used to prepare the rocket for launch. Pinpointing targets 200 miles away was a formidable challenge that V-2 engineers tried to overcome. V-2 launch crews had to rely on specially prepared maps and precise triangulation of the launch position. Next, the V-2 needed to be fueled, but before the tanks were filled, the crew performed a dry purge of the tanks with compressed nitrogen to ensure that there were no leaks. First, the fuel tank was filled, followed by the liquid oxygen, and then the remaining tanks, 2 for the steam generator and several small nitrogen tanks. While still resting on the firing table, external electrical power would be supplied to the V-2. After fueling, the ground crew checked again that the V-2 was perfectly vertical and properly oriented. Finally, the hatches would be closed, the lifting frame lowered, and the Milewagen moved away from the site. The firing crew then connected the electrical igniter to the combustion chamber and signaled that the rocket was ready to launch. The troop commander would order everyone to clear the site before he entered the command vehicle, where he would give the order to begin the launching procedure. Inside the rocket, everything was set. The pressurized nitrogen forced the hydrogen peroxide and sodium permanganate into a steam generator, causing the two mixtures to react and produce high-pressure steam. That steam powered the turbine inside the turbopump to spin at 3,800 RPM. Each second, the turbine pumped 158 pounds of liquid oxygen at a pressure of 17.5 bars into the combustion chamber. It also pumped 127 pounds of fuel at a pressure of 23 bars. Inside, the mixture was ignited and brought to a temperature of 4,532 degrees Fahrenheit at a pressure of 15 bar. The ignition sequence did not produce enough power to launch the rocket. It only served to give the control officer an indication that the engine was working properly. If everything was in order, a switch was activated for the turbopump to increase its speed to 5,000 RPM, causing the engine to produce a thrust of 55,000 pounds. The electrical cables would disconnect electromagnetically and the rocket would lift from the ground. The amount of fuel and liquid oxygen in the rocket's tanks allowed the engine to burn for no more than 70 seconds. At maximum power, it produced a thrust of 64,000 pounds, resulting in a staggering speed of 3,580 miles an hour, just under 5 times the speed of sound. Hi, I'm David Webb. I'm the head of Yarn Hub Animation Studios, who produce Blue Paw Print. Right now, we're offering our viewers a chance to buy shares in our company. So if you think our films are important and you'd like to see more, as well as help fund our move into gaming, you can share in the future of Yarn Hub. Click the link in the description to find out more. During the ascent phase, the rocket was steered by 4 external air vanes and 4 internal jet rudders. The external vanes were conventional vanes connected to the fins, while the internal rudders were placed in the exhaust gases. Because of the intense heat produced by the exhaust, these rudders were made from graphite. After liftoff from the pad, the V-2 would travel vertically until it gained enough speed for the air rudders to work effectively in tandem with the jet rudders. After 5 seconds of vertical flight, the mechanical motor would tilt the gyro that controlled vertical pitch. This signaled to the rocket rudders to slowly pitch the rocket's nose downward. After 25 seconds in flight, the V-2 would break the sound barrier and go supersonic. At 54 seconds in flight, the missile would be 49 degrees from vertical. At this point, the V-2 has enough speed for the air rudders to be effective without using the jet vanes. Another gyro controlled yaw and kept the rocket on course by using graphite jet rudders first, and then jet rudders and air rudders. If, during flight, the gyroscopes detected any deviation in pitch, yaw or roll, they could send an electrical signal to the analog computer, known as the Mischgerät or mixing device. The Mischgerät would then calculate the necessary corrections to keep the rocket on its projected trajectory, and send computed adjustments to the external air vanes on the stabilizer fins and the jet rudders in the thrust's airflow. To follow the predicted trajectory, it was crucial for the rocket to cut its engine at the designated moment. The device controlling the cutoff was called the Pendulous Integrating Gyroscopic Accelerometer, or PIGA. Once the rocket reached a predetermined velocity corresponding to the desired range, the PIGA generated a signal to start the engine cutoff procedure. Once the engine had cut off, the rocket acted similarly to a regular artillery shell. It flew along its ballistic trajectory with just the air vanes keeping it on course. At this point, the rocket's angle of elevation was approximately 40 to 45 degrees. Even though the guidance system was sophisticated for the time, the V-2 was not a precise missile. At maximum range, the deviation between the target and impact was between 4 and 11 miles. Because of this, the V-2 was suitable only against large populated areas, such as the City of London. From September 1944, these rockets started landing on London. The impact of the V-2 missile was a horrific experience. It seemed to strike from out of nowhere. The first thing to be heard was a devastating explosion, followed by a huge cloud of debris. The roaring sound of the incoming rocket arrived only after the blast. The violent tremor caused by the explosion could be felt from nearly half a mile away. After the war ended, American, British, and Soviet engineers showed particular interest in the V-2 development program. This interest was driven by the fact that the V-2 introduced several key innovations in rocket engineering, specifically in the design of the rocket engine. While the V-2 missile was a revolutionary design, it was not as effective as the Nazi leadership had hoped, and it was not the wonder weapon that could change the tide of the war. It was too expensive to be efficient, with the average price of a single V-2 missile slightly over $1 million in today's money, which was 20 times more than the cost of the V-1. If the V-2 had been introduced 2 years prior, before the Allies had landed in France, the Germans could have used it against British ports to slow down the invasion preparations. Being operational only in the autumn of 1944, it was simply too late. Despite its drawbacks, the legacy of the V-2 was immense. The technical solutions introduced were applied in rocket designs for decades to come. Sergei Korolev, the key Soviet rocket engineer and spacecraft designer, used many elements of German rocket designs for his own research that ultimately resulted in sending the first artificial Earth satellite, Sputnik, into space. On the other side of the Iron Curtain, Wernher von Braun, one of the fathers of the V-2, became a leading figure in the American space program. If it wasn't for him, the moon landing in 1969 might not have been possible. As well as the V-2, there was the lesser-known V-3 London gun. Please watch our video on this incredible weapon. It was a lot of work to dissect such a complex machine as the V-2, and we still had to leave out many details. If you find any errors, please let us know in the comments. Thank you.